Okay. Hello, everybody. And so I will remind you what I was doing yesterday. I discussed this procedure of truncation or smearing of charges, from points, Dirac masses being replaced by uniform charges on spheres. And that allows to rewrite the modulated energy in a very general way for all configurations of points and all densities rho as a difference between an integral term, so here, an integral term of this form and a very large compensating term of this form, where here the eta i's are these truncation radii that I chose. And I explained yesterday the monotonicity with respect to the truncation parameter. And the fact that if you pick these radii to be equal to the minimal distance or 1/4 of the minimal distance to the nearest neighbor, then it makes disjoint balls. And you have the advantage that now you can control separately the two pieces of the energy. So where the energy is defined as a sort of difference between something like this and something like that. Okay, and so with that, I showed you that this modulated energy, even though it's not positive, it's bounded below by something that's little o of 1. So it's almost positive. And I told you when I stated the theorem, it's not clear that it metrizes weak convergence. So it's not obviously clear it's a good metric, but now we can show it's a good metric. So with this, we can show that Fn is a good metric indeed. If you take, let's say, take a test function. And you want to take the soup over such test functions of something like this. So the empirical measure minus rho. So how can you estimate this via Fn? Well, what you can do is you can replace this by the smeared Diracs. So let me take Ri here as the radii. And then, of course, I have to correct. Okay. And so the first term, I can rewrite it as the integral of phi times the Laplacian of my function hn with truncated at radii ri. And of course, there is a -1 over cd, but that's not very important. And the second term, I can estimate it so it's just 1 over n sum of, so I can just quickly estimate it as basically the Lipschitz norm of phi multiplied by the max of these ri's, right? Because if I integrate phi over the sphere of radius ri, or if I take phi of xi, the difference is at most this, and I have n terms, I divide by n. So this is this, right? And now for the first term, I'm going to estimate it by doing integration by parts. So I'm going to do constant times grad phi in L2, grad h n r in L2, plus a constant. And the max of Ri, I told you I maxed it at n minus 1 over d. So even if the points are very far from each other, we don't want this to become too large. So this we can just bound by n minus 1 over d, norm of grad phi in L infinity. And now we're almost done, because you see, I told you here, this thing is controlled by f. So up to a small additive error, I have this controlled by two. And so now I can put Fn, Xn rho. And maybe in dimension 2, I have this n over 2, sorry, 1 over 2n log n. But that's actually okay. Plus n to some small, a small term, that's the negative power of n, plus c quad phi n minus 1 over 2. Okay, so I give you a crude estimate. You can try to optimize it over the test functions, maybe not take Lipschitz norms, but C0 alpha norms if you want. There's many possible choices, but you see that this gives a good metric for convergence. By taking a soup over all test functions, you find that there is some functional space. Such that the norm of the difference between the empirical measure and rho in this space, so let's call it x, that is less than, and I forgot there is a 1/2 here. Here I should have a 1/2. That. So here I will have c, of course, essentially square root of Fn plus little over 1. Okay, without being too explicit, some negative power. Okay. So that allows to have the second part of the theorem where you say after you prove your Grandval inequality, you show that Fn is small, when that implies indeed convergence of the empirical measures, thanks to this little argument. Okay, so now what remains is to look at this functional inequality that we have to prove. So I remind you what this was about, called also commutator estimate. So scrolling up. It is this inequality, right? We have to prove this. And if you want, you can view this as a commutator in this way. And we have seen in the Courant case a sort of formal proof brought by the stress tensor, the stress energy tensor. So in the when I showed you this thing, I showed you that you can rewrite this formally like that, and that sort of indicates that there's a proof this way, but you have to take care of the removal of the diagonal. So these singularities, these Dirac singularities, and we're going to treat them by this truncation procedure. Okay, so let's go back now to the quantity that needs to be estimated, and I won't give you all the details because it would be too long, but just a flavor. So now, how to prove the commutator estimate. Let's say in the Coulomb case. So or Rees S bigger than Z minus 2. You remember you do that with the extension and adding the weight Z to the power gamma. So everything's the same, but with weights. So we have to look at this. So I'll write it again. V is some Lipschitz vector field. And we're doing that. Why? We'll just do this. So we're going to use the same idea as for defining the redefining the modulated energy, which is that I'm going to write this as the limit when eta I all go to 0 of v of x minus v of y dot grad g x minus y. And let's replace these Diracs by these Diracs on spheres, right? So certainly this is okay. For fixed n, you know, I can take eta go to 0. But so what we're going to do is we're going to put back the diagonal, but then remove it because we're making a mistake. So what is that we have to remove? Well, we have to remove sum from 1 to n of integral v of x minus v of y dotted grad g x minus y. And I have a 1 over n squared. Maybe I'll put it here. 1 over n squared delta xi eta I of x delta xi eta I of y. Okay. So now that's good because now I have my double integrals, and I can hope to apply the same type of calculus as I did before. So really, let's do it. We can do it. So the first term, you remember by desymmetrizing it, we can find that it's twice. So you split it as v of x dot blah minus v of y dot blah. You swap the rows of x and y in one of the integrals, and you find twice the same thing. So you find actually twice integral v of x dot grad g x minus y d 1 over n of delta xi eta I minus rho of x of y. Okay, and here we can recognize a convolution. There is g convolved with this. So now this is really two integrals, so it's a single integral. And I'm going to recognize the gradient of h and eta of x, because that's what I get when I convolve g with this truncated measure. And then I just have one sum to do. Right? But now we have exactly the structure we had seen before. This is the Laplacian of h and eta up to minus 1 over cd. So I can rewrite this as minus 2 over cd integral of v dot grad h and eta Laplacian h and eta. And this structure we have seen, that's exactly the divergence of the stress tensor. Okay, so I continue with my role of equalities. This is equal to 2 over cd integral of derivatives of v dotted with this tensor grad h and eta. All right, so now I have my difference. So let's call this the term we're trying to estimate, big one. All right, so big one is going to be the limit as eta I goes to 0, all eta I go to 0 of this term. minus the sum of terms that are all of the same type, and you can rewrite them as also in terms of some stress tensor in the same way as you did before, but so there's a stress tensor of something. It's not h, but it's some other function that's kind of explicit. So I don't want to give an exact formula, but you can find this all in my paper, of course. Okay, so at this point, we would be happy, we would be good in some sense if here, instead of this eta that go to 0, and we don't know how fast they need to go to 0, if we could replace eta by r, right? So if we could replace eta by this vector of minimal distances, then we would just need to control a term that looks like this, tv dot quad h and r. And this term, I can bound it immediately by the Lipschitz norm of v multiplied by the integral of quad h and r squared, because you remember the stress tensor is quadratic. So point-wise, you have this bound. And this thing we control by the energy. So remember, we control each piece, you know, of the difference. And what is the goal? The goal, you remember, is to bound I by Fn. So for this part, we have exactly the estimate we want, the Lipschitz norm and Fn. The other parts, it's also okay, in fact. So, the other part, we control it. And I don't give you details, but if you take R, it will be controlled by the norm of dV in L infinity times the sum of G of Ri's. And that again is controlled by F. These are my two controls from above. So we would be good, right? So we would be finished. But the problem, of course, is that this thing now, it's a limit as eta I goes to 0. It's not equal to the value at Ri. So we have to understand how this term varies as you vary the eta I. Okay, so this term. Okay, so we have to work. So let's call this term T sub eta. I have enough space. I will call this term T sub eta. So basically all that's left to do is to control the difference T sub eta minus T sub R. Right, so how does this thing change if I increase the size of the balls? And this time I don't have a monotonicity property anymore. When we were discussing the energy, there was a certain monotonicity. This one, it's not monotone, but however, you can control this in terms of the Ri's and in terms of the energy. And you can show that it's actually small. So it's a small additive error. So it's going to be controlled by some powers of n and Fn itself, some negative powers of n and Fn. So I won't say more. But if you go back to the estimate that was to be proven, that gives the proof, and you will see here, you don't control just by the energy, you have this additive error. And the additive error comes from this this error in variation of the radii. So That's it. So I've pretty much given you I take a flavor of the proof for the Coulomb case. Now, if you want to do super Coulombic, I said you do just with the extension procedure and the weights, not really a difficulty. And now, what about the more general case, and what about the subcoulombic situation? So this is the work that we did in this paper with Hung and Nguyen and Matt Rosenzweig. And for that, we went back to really looking at this term as a commutator. So you remember that we can look at we can rewrite the term that we're looking at. So let's now do it in a slightly more general form. Right, so let's just call df of x, df of y. The difference between the Diracs and rho. And this you can rewrite as a commutator. So you have d minus s over q. Right, so there are two steps. The first step is to, so again you want to use smearing idea. So again, use smearing to replace the Diracs by some Diracs, some uniform measures on balls. Let's say this time it's not so important to have spheres, but you can do just balls of radius eta. And what you're going to lose in this case, which is not Coulomb, is you lose Newton's theorem. Because Newton's theorem is specific to Coulomb. Newton's theorem, I remind you, was saying that if you have a point charge and you look at the potential that it generates somewhere, it's the same as the potential generated by any uniform, any radial distribution centered at this point charge. So seen from outside the distribution, it's the same. But if you have a general interaction G, interaction kernel, it's not true anymore. So what we have here is we're going to first assume that G is 1 over x to the s, where s is less than d minus 2, because this is the case we haven't treated yet. And observe that this kernel is not harmonic like the Coulomb kernel. It's not harmonic away from the origin, but it is super harmonic. Super harmonic. So super harmonic means the Laplacian has the positive, the negative sign. I don't know. Yes, negative sign. And in particular, it means that if you convolve G with a smeared Dirac like this, it will be less than G. So that's not too hard. It's a property of superharmonicity. Superharmonicity, you can rephrase it in terms of mean value property, right? Harmonic is value of the function at a point is equal to its average on spheres or balls, and superharmonic, well, the value is bigger than its average. Okay, so that's what you get from that, and that's going to give you that when you smear, well, you don't have an equality, but you have an inequality. Okay, so that's the point of the smearing. So when later we want to generalize, and I can say it right away, when generalizing to non-exactly Riesz interactions, we're going to want to retain this feature of being superharmonic, but only near the origin. It doesn't matter that you're superharmonic everywhere. So we need just to require G superharmonic in a neighborhood of 0, some fixed neighborhood. Okay, so that relaxes a bit the condition. You don't have to be an inverse power, just need to keep this. But then there is an observation which we used, and I think is cute, is that if you now consider G equals 1 over x to the s, for instance, when s is bigger than d minus 2, it's no longer superharmonic, it's actually subharmonic, so it goes the wrong way. But when you compute the Laplacian of G, so that's something I never remember the exact formula, but there is a d minus s or something. You notice that if you were in larger dimension, this function, which is subharmonic dimension d, would become suddenly superharmonic. So it's just a matter of making the dimension large enough. I think there's d minus s minus 2. So there's a certain sign, and when s is bigger than d minus 2, it's the wrong sign, but so this becomes superharmonic in large enough dimension. In other words, what that means is we can consider an extension, just like before we had extended dimension. It's the same procedure. You can consider a large enough dimension m bigger than d. And you can consider an extension of G, so natural extension, just keep the same inverse power. And now G has become automatically superharmonic in dimension n. Okay, so everything you were doing in RD with the points and the blah and the background of probability, you can just embed into Rm, and you can just rewrite it with the big G. It's not going to change anything because the Diracs won't see the difference. And here, rho tilde will be just an extension, like rho delta RD, basically, of your original density. So it coincides. It coincides with the previous definition. It's the same as this. But now you have a superharmonic potential. And so you can do these smearings. And so the point is, we can do the smearing in the extended space. So now these balls you see that you draw around the points, they're going to escape RD. They're going to be, you know, they're going to be like this. So you see, okay, my drawing is not super good, but you have to imagine these balls in extended space. Okay, so you do the smearing in RD, and you retain the monotonicity properties that are needed. Etc. So this allows to treat fairly general interactions. So of course, all these inverse powers now, all the way to D. So whether S is less than D minus 2 or bigger than D minus 2 doesn't matter anymore, because by extension of dimension, you always fall back to a superharmonic case. And you can also treat more general G's by just requiring the superharmonicity near the origin. But the other constraint that you have is you still need F to remain a metric. You need F to remain some sort of metric, right? So if you remember what F is, when you do a double integral of G, X minus Y, df of X, df of Y, in Fourier terms, this is the same as integral of G hat F hat squared. You'd better ask that G hat has some positivity. Otherwise, this is not going to be a metric. So in fact, we also ask that G hat does behave like the Fourier transform of a Riesz potential. So like the Fourier transform of 1 over xs, which is 1 over c to the d minus s. All right, so in other words, what you ask more or less, the conditions are, there exists an extension big G of little g to a space of higher dimension such that big G is superharmonic near the origin. And G hat of C, is bounded above and below by what it would be if it was Riesz. So I should say 2-dimension M. So here you would have M minus S. For some S, of course. All right, so you want to retain a little bit of those features. And there's a few other conditions which also are of nature of G having the same type of decay as the Riesz powers. But it gives a bit of more flexibility, right? So instead of being exactly an inverse power, you can have a little bit of wiggles along the way. It's not so important. Okay, so that's the first step, which consists in doing the smearing. And after you've done the smearing, basically, after the smearing is done, we have to look at things like this now. Big G or little g, doesn't matter. So these are the smeared things. Okay. So we have to look at this and then look at the difference. So what we call renormalize the estimate. By bounding the error. So the error made by just the difference between the two. Rho. So that's done differently than I showed you in the Courant case. So in the Courant case, we look at a sort of replacing eta I by Ri and using the stress tensor. Here, this is done a little bit differently. And here I have the diagonal removed. Okay, so this error will have to be controlled. But once you've done that, you reduce to understanding things like this. Okay, so assuming this error is bounded, there remains to bound this by F. And now we have a more standard commutator situation because we don't have a removal of the diagonal here. We have a true genuine double integral. So a more standard commutator estimate situation. No diagonal. All right, so at this point, we could have tried to use some off-the-shelf commutator estimates from the harmonic analysis literature, which involve actually pretty sophisticated things like paraproducts and things like that. But we got a proof that's more direct, much more space-based. There's no complicated Fourier analysis. So I want to give you our proof. And the important part in this is that now the proof is not going to rely on stress tensor. Stress energy tensor. And that's important because that's how we can generalize to this class, this broader class of interactions. You've seen the computation that's at the heart of the stress tensor argument is really using the Coulomb nature of the interaction. So that the fact that G is the fundamental solution to the Laplacian or to a divergence form operator if you use the extension procedure. Now there is no stress tensor, and there is also no pair product or whatever product Fourier harmonic analysis argument. But interestingly, the proof is going to be the most difficult in the Coulomb case. So you see, when you have the Coulomb case, it's much better to go to the stress tensor. And when you want to go this route with commutator estimates, the Coulomb case is actually the delicate one. So here are a few steps. Right, so you want to write RD plus RD. So I can write it in extended space or in normal space. It's the same argument. So let me just write it in normal space with a general function here, f of x, f of y. And it's just integrations by parts, honestly, but very careful ones. So what you want to write is you want to write f as the divergence of something. You can always write f as the divergence of the gradient of the inverse Laplacian of f. Why not? Because divergence of the gradient is the Laplacian. That's going to be this. So you can write it as a divergence of something. Right? And so now you start to write this as integral of something. So just put everything in a kernel. Right? All this kxy. And now you have div f1, div f1 of y, and start to integrate by parts. Right? So when you integrate by parts, you're going to put the derivatives on k. And but k, you know, you have an explicit form for it. You see how k behaves. Interestingly, k, the derivatives go on k. K of xy. If you think of g as an inverse power, so g is like 1 over x to the s. When you take the gradient, you have an extra power, 1 over x to the s plus 1. But when you multiply by v of x minus v of y, you regain a power x minus y, right? So g of xy has the homogeneity of g of x minus y. At least when x is close to y, and so for g inverse power. And with the assumptions we put, we have this. And this is because v is Lipschitz. Okay, so actually, I should have said this earlier, because this is the reason why the estimate that we're trying to prove, this commutator estimate, this is the reason why it's plausible. Right? It's plausible because, well, this thing, even though it's not g of x minus y, it has the same homogeneity. And when you have g of x minus y here and sum of Dirac minus rho, sum of Dirac minus rho, this is f, this is the big F. This is the modulated energy. So from a sort of Fourier point of view, or from this point of view, the commutator estimate is credible. However, you can't make that into a proof, because if you try to make the estimate like this, you're going to have to estimate the absolute value and then put the absolute value inside here. But then you're making the absolute value also here. And by doing that, you're killing the cancellation between the Diracs and the rho. Right? So if you do that, you get something where you have a 1 over n sum of Diracs plus rho instead of minus rho, and then you cannot fall back on the modulated energy, which definitely uses a cancellation. Okay, so you do know, however, how k is going to behave. So when you do your integration by parts, you see what types of terms you get. So the reason that I said that you can't do this abruptly is why we need a whole proof here. That's what we're doing. And so after you do that, you put the derivatives on K, you do some symmetrizations of the integrals in terms of X and Y. And you find yourself with showing that your first term that you're trying to integrate is bounded by the Lipschitz norm of V. So that's going to come out when you estimate the derivatives of K. And you're going to get terms like this. Yeah, and so if you're good in fine analysis of Sobolev spaces, in fact, you can recognize that these sorts of double integrals here are one of the definitions of fractional Sobolev spaces. So this is really equal to the Lipschitz norm of V times some Sobolev space, so it's H dot S minus D over 2 square norm of F. Okay, so even though it's F1 that comes here, there's a relation between F and F1 and F, and you can bound by this. And this is exactly, well, if you're lucky, this is F. We've said this before. This is like Fn, except for this story of the renormalization. I think we should just mute. There's like a word mute. Except for the removal of the diagonal, etc. Okay, but remember here, we're not going to work with the true Diracs. We're working with the, so here F is not the thing with the true Diracs, it's the thing with the smear Diracs. So that's actually okay. So what you have to show is what I've alluded to, we've done already in the Courant case, is you have to check that this in this norm, that's controlled by F. So in the Courant case, I've showed you how to do it, because this is rewritten in terms of a, so this is a squared. This is rewritten as a integral of grad H squared, blah, blah, blah. Now in this more general setting, it's not quite the same, but it's part of the preparation, you know, this sort of smearing preparations includes proving that this is true. Okay, so once you arrive at this estimate, you're happy. So this is actually, I've described to you the case S bigger than D minus 2. So this is for S bigger than D minus 2. When S is equal to D minus 2, you're sort of in a borderline case from the point of view of harmonic analysis here. So you can't quite go from here and straight to this. And you need to finish with some theorems from harmonic analysis. So I told you, please join. I mentioned that we're going to use them at some point. But somehow, if you're exactly Coulomb, it's much better. It's a much quicker proof to use the stress tensor. So this is when you want to relax a little bit the Coulomb case. Okay, and when S is strictly less than D minus 2, you have to do the same integration by parts idea, but you have to iterate it. So we need to do iterated integrations by parts. plus Riesz transform estimates. Okay, so that's all I wanted to say on this presenting this this commutator estimate. That sort of concludes one part of the story, which is the part with no noise, right? We haven't discussed noise so far. We've just discussed first order mean field limits and a little bit the second order in the monokinetic case. I mentioned there is another part now of new results with Matt Rosenzweig where we obtain global in time estimates. So by improving the Grandval argument, exploiting the decay of the solution as time goes to infinity, you can actually get global in time. So I will just mention this. So global in time convergence results with Matt Rosenzweig. What they do is they exploit again this functional inequality, the commutator estimate, by looking a little bit at the dependence in all the various quantities. So we have an optimized version of the commutator. So it exploits optimized version of the functional inequality. And what is it? Is this? It's the integral. And so now we have Vt. And I write Vt because now I want to remember that this V is the one that comes from the solution of the limiting equation. And this is less than C rho T infinity S plus D over 2 Fn of x and T rho T plus some negative power always S over T minus 1. So here rho T, right, solves dt rho T plus convergence K convolved with rho equals 0, and Vt is the velocity K convolved with rho T. Right, so in the standard commutator estimate, you have the norm, you have the Lipschitz norm of V as a multiplier here. So here we're sort of estimating better how the Lipschitz norm of V depends on the solution itself. And now you see that when you do your Grandval, so now Grandval is, right, so dt of f, x, and t rho T is going to be bounded by this commutator term. So by exactly this commutator expression. And so it's bounded by C rho T S plus T over 2 L infinity Fn plus something small. And so now this term, we can exploit its decay in time. So decay like 1 over T to some power. So as long as you know some decay, like this. So I think here we do this and maybe we add the noise. Whatever, but it's just to show you that if you know some decay in time, then when you plug that into Courant value, you know, you're as long as this this thing here, this function is integrable in time at near infinity, then you will get actually a global in time control. So you apply Courant val. So instead of the exponential in time, you get a uniform in time. Estimate. So it's much better. So again, that comes from looking more carefully at this commutator estimate. So for us, we prove this decay in time with a proof that's in. So we had to make the proof, but it's inspired by Carlin and Loss. So these are, of course, PDE questions, right? You just you have to look at this PDE and see how the solution behaves, and then you can exploit that. So, as I said, this is the end of this part, and starting in the next lecture, what I want to do is I want to discuss the case with noise. So I will show you what can be done in the case with noise, the relative entropy method, and the modulated free energy method. And I think it's a good time to stop for today, for this afternoon.